It is equivalent to a generalized linear model. For example, if the activation function is sigmoid, it becomes logistic regression or multivariate logistic regression in this case. And so it is very important to note that a neural network without a hidden layer is just like a linear model. It's just like a regression model. So one may say that there is no point to use a neural network with no hidden layer. The power of neural networks comes from the hidden layers. So we should have at least one hidden layer for the network. And so without the hidden layer, essentially it is equivalent to a linear model and a generalized linear model, a generalized linear regression. With the hidden layer, then we have nonlinearities involved. So we can have nonlinearities involved if the hidden layer has a nonlinear activation function. But I should mention that if we have a hidden layer and it does not have a nonlinear activation function, still we have a linear model. Still we have a linear transformation. It is equivalent to linear transformation. However, if the hidden layer has fewer neurons than the input layer, essentially we are doing a dimensionality reduction here. So it becomes something like PCA, principal component analysis, except it is supervised. It is kind of supervised learning. So it is more closer to PLS. And it is essentially a kind of supervised exploratory factorial analysis. That's how it can help, but still it is linear. So the power of neural networks comes when we have nonlinear hidden layers, or at least one nonlinear hidden layer, one hidden layer with nonlinear activation function, with a nonlinear activation function. And it is actually proven that a neural network with one hidden layer that has a nonlinear activation function can approximate any function in the world. So any continuous function in the world. So it is universal approximation theory. And that's what makes the neural network so powerful. So for example, if we have just ReLU, which is a very simple nonlinear activation function, if we use ReLU, you see that combination of several ReLUs, we can approximate different bends and different shapes of functions. So it depends on where we put the ReLU, at what position, and with what weights, So essentially, we can approximate any function using just a series of ReLUs. Essentially, what we have is actually some kind of piecewise linear regression model, except the breakpoints also are variable. The breakpoints also are optimized. So it is more powerful than piecewise linear regression, and we don't need to manually set the breakpoints or determine where the lines should be. So so this enables us to approximate any function, even very complex functions, with one hidden layer. But if we have more than one hidden layer, for example, we have two hidden layers, it becomes even more powerful. So the neural network can approximate orders of complexity. And essentially, we can have many, many hidden layers, and that's hence the name deep neural networks. So how can we train a neural network? So the neural network is composed of a set of weights, essentially. So the linear transformation would be just some kind of weights. And the main power of neural networks is that when we use traditional models, when we feed them more data, at some point, the model is saturated and it doesn't have more capacity to learn better and do better and have more predictive power. But neural networks have a lot of capacity, have much more capacity to learn and improve their predictive performance. So, however, we should be very careful that in one hand, of course, if we don't have many parameters, if we have a simple model, of course, we are underfitting, and we do not have enough capacity to learn. We talked about it, but On the other hand, if we have too many layers, too many neurons, we have too many parameters, and we may overfit to the training data. That means the network is learning and memorizing the data. It's memorizing the data along with the noise. It is not learning the patterns. So we should not have too many parameters either. So we should have the right number of layers and parameters. So if we have too many parameters, too many layers, of course, we may have even worse performance even in the training data. So how do we do the training in neural networks? It's very straightforward. We have some training data. We put the inputs, the neural network. We first start with some random weights. The W's are the parameters that should be optimized. We use the initial weights to find the output, to calculate the output. We compare the output to the ground truth, to the to the outputs that we have from the training data. And after comparison, we get some sort of error. And then based on the error, we are going to adjust the weights. And we go through this process several times until the weights can result in reasonable outputs that are close enough to the ground truth. So essentially what we do is that we compare the calculated or the predicted output to the ground truth, to the output that we have in the training data. And we do that for all the training data and average them. We can average the differences over the training data, and that would be our loss function. So the loss function is what we are trying to minimize. And the weights are essentially the argmin of the loss function, the argmin of the average of for the loss function. So essentially, we are trying to minimize the loss function, and through adjusting the weights. The optimal weights are essentially the resulting neural network, the trained neural network. So there are two main loss functions. One is mean squared error, so which is what we use in regression, in just regular regression, linear regression. And the other one is binary cross entropy, which is very similar to what we have in logistic regression. And when we have continuous output, we use MSE. When we have binary output or classification, we use binary cross entropy. If we have multi-class classification, we use just cross entropy loss. So the mean squared error is uses the same formula as we have for the linear regression, multiple linear regression. It's straightforward, just the sum of the squared errors. And the binary cross entropy loss uses the log of the calculated or predicted probabilities times the actual ground truth values. Of course, the ground truths would be binary, would be 0 and 1, but the predicted values would be probabilities. So comparing them would be a little bit tricky, but there is a formula for that. And it is much better than MSE for binary outputs. So it can easily be verified that minimizing the binary cross entropy is equivalent to maximizing the log likelihood that we do in logistic regression. And that is exactly why the multi-perceptron that we saw is equivalent to a multivariate logistic regression. So how do we just adjust the weights once we have the loss function? So we define the loss function, we have the loss function for the model. To adjust the weights, we should compute the gradient of the loss function with respect to the weights, particularly the partial derivative of the loss function with respect to each of the weights. So based on that, we adjust the weight. So of course, we adjust the weight in the opposite direction of the partial derivative, because the partial derivative or the gradient directs towards increasing the loss function, but we want to minimize the loss function. So we move to the opposite direction, and essentially we find the optimal values for the parameters of the network. So I have a question. We see that in when we use the partial derivatives, we essentially what we do here is that we reduce the parameter proportional to the partial derivative. Of course, it is multiplied by some factor, its learning rate, but given a specific learning rate, it is proportional to the partial derivative, the amount of adjustment. So my question is that, should it be like that? Should we adjust proportional to the partial derivative always? You see that if the partial derivative is small, it is possible that we have to go a long distance to reach to the minimum point. On the other hand, it is possible that the partial derivative is large and we are very close to the minimum point. So is it reasonable to adjust proportional to the partial derivative? Any answer? Any suggestion? So the reason that we do it proportional to the partial derivative is that we usually have many parameters, and the partial derivatives give us the direction towards the minimum in the space. We calculate the partial derivatives to find the direction towards the minimum point. But how much should we move towards the minimum point? The distance that we move should not necessarily be proportional to the gradient. So, and what we need, the direction of the gradient is important, not the magnitude of the gradient. That's very important to note. And the modern method, the new methods for optimization, some of them actually normalize the gradient. So we have normalized gradient descent methods, or methods like Adam, they just adjust for the magnitude of the gradient. So the magnitude of the gradient is not an important number here, is not important value. The direction of the gradient is important. And we use the partial derivatives to find the direction of the gradient. So I should mention that usually when we have a large data set, when we have a large training data set, it takes a lot of time to train the neural network just using all the data, all the training data. It is not reasonable to do that. So what we do is that we use batches or mini batches of the data to just train the network. And after several batches, we cover all the training data. So in each batch, we just adjust the weights after each batch, and then we just do another batch. So the batches are just selected randomly. So we take a random sample of the training data to create a batch, and then adjust the weights based on that. So this randomization actually introduces some randomness in the direction of the gradient. That is why they call it a stochastic gradient descent. So a stochastic gradient descent has proved to be more powerful and more efficient than just deterministic gradient descent. So the size of the mini batches actually is a hyperparameter that should be determined by the researcher or the person who is using the neural networks. So empirical studies have shown that the stochastic gradient descent actually performs much better throughout time than the deterministic one. So far we talked about using the data and everything, but how do we calculate the partial derivatives for the weights, for all the weights? For the last layer, it is easy. We have the activation function, and we just take the partial derivative with respect to the activation function, etc. But what about the previous layers, the earlier layers? For that, we should just use the chain rule. The chain rule. We know that each layer depends on the previous layer, etc. So these dependencies, the values of the outputs depend on the previous layers. It helps us to just find formulas for the partial derivatives of the loss function with respect to all the weights throughout the network. So that's why it's called backpropagation. Essentially, we have the loss function at the end. We find the partial derivatives with respect to the first layer, and then with respect to the next layer, and then the next layer. So with respect to the last layer, and then next layer, and next layer, and then the first layer. So that's so it's all about partial derivatives. So we need to consider something like memory. Essentially, we need to do sequence modeling. So in sequence modeling, we can have a series that predict one thing, or one thing that predicts a series, or a series that predicts a series, etc. We have different situations. RNN, or recurrent neural networks, are the neural networks, that a type of architecture that can help us work with sequences and do sequence modeling. That is important when we have a variable length of inputs. So we don't know how many inputs we have, or we have dependencies across the inputs in the sequence. So we need to have some sort of memory in the network. And for that, what we do here is that we have a hidden state in the neural network, and the hidden state is fed into the next step. So it is actually updated with each round of using it. So it is what happens is that when we are using the neural network, each step is not independent from the previous steps. So each step, the neural network essentially changes and learns dynamically, learns or stores some information. So considers the information from the previous steps. So essentially, we feed the information in steps, in series, to the neural network. And it is like if we unroll it throughout time, it is like we are feeding the inputs to the network, and then the hidden state, the value of the hidden state, is also fed into the network the next step. So essentially, we have two functions. One function that adjusts the hidden state, and by function, I mean like activation function and linear transformation, everything that we had before. And one function that gives us the output. So the output is a function of the hidden state as before. So this picture, I think, shows it better. We have this is called Elman network. So in each step, we store the values of the hidden layer into some context nodes, some kind of memory. And in the next step, the values of the memory are fed into the network, are fed into the hidden layer, along with the input values, the new input values. So we have some kind of memory here. And there are several problems with RNN. First of all, when we want to train it, we have to consider all the losses, and the backpropagation needs to consider the sum of all the losses throughout time. And this makes it difficult to find the gradients, the gradient or the partial derivatives for the W's, because actually we have to find the partial derivatives throughout the time for all the steps. And that can result in vanishing gradients or exploding gradients, because you are multiplying a number by itself multiple times, because you have the same weights and you are just multiplying the weights multiple times. I think I ran out of time. I have a lot more to cover, but so